Okay, welcome to the Monday 4377 networking class. We talked about DNS last time, and we went in excruciating detail over an example where in order to find the IP address of a computer at not only another location, but one that ends in a different suffix, like .org instead of .edu or something like that, we ended up working our way all the way up to the root level directory, DNS directory. But in general, what you'll do is the odds are that you will know all of the popular top-level domain addresses, so you can go to them directly and ask, what's the one for whatever site you're trying to get to? That's one thing you usually have in your cache at your administrative DNS server. The other thing you usually have in cache are all the popular sites, google.com, amazon.com, et cetera, et cetera. So it's not enough just to know one. The actual fully qualified host name, like server3.rack4.utah6.google.com, is a separate DNS entry than any other variation of that string. So it could be the pointing to the same server as 100 other strings, aliases all to the same one, or it may be the only name that was ever put in DNS for that particular IP address. But you have to go look it up. Once you do, you cache it for a while. All right, so to kind of step back then and to go through that example with a different diagram, the one that the book uses, we'll look at two different ways of going about this. And I used to think for the longest time that no one ever did a recursive query, but I think I'm wrong. I think I found some examples of it. So we'll talk about both of them. I used to kind of ignore the recursive example, but let me show you what this is basically saying. CISpoly.edu wants to make a connection, TCP, let's say, doesn't really matter what type. They've asked, the user has asked for a connection for a packet to be delivered. And in order for the packet to be delivered, the application must provide the transport layer, layer 4, the IP address of the host. And like we talked about before, that's very non-intuitive. And the reason why I say that is because if you draw the 5 layers, you have your application up at the top. It deals in messages. You have the transport layer down below, TCP and UDP, as we'll learn. And then the IP layer, which is the network layer, lives below that, data link and physical. All right, IP layer is where IP addresses exist. Well, duh. That's why they call it that. So if you want to know how do I get to a certain IP address, the IP layer will tell you the answer to that. If you want someone to figure out who can I see from here, who's nearby, the IP layer runs a program that will figure all that out. So you would think that you could show up at the IP layer and go, what's that funny number that you like to use for this host, and it will tell you. If that were true, then application authors would just make their function call to the socket library they want to use, and they would just pass the name of the host in there. Well, that doesn't work. You have to have the IP address. This will not work. So for the IP address, you're going to have to run a name resolver, NS, resolve. There's a bunch of different names depending on the operating system. But basically, it's a program, a function that you call. You give it a name, it gives you back the IP address. So running this, in order to get this, is what this diagram is showing is happening. So all the DNS lookups that you see are all caused by some app realizing it needs to know the IP address, and so it asks DNS for help. Once it gets the answer back after the end of that whole thing, now it can make the socket call and start asking the transport layer to kind of help get there. So there's a chicken and egg kind of thing here, right? Because before the app can go to the transport layer, it has to have the IP address. How do you get the IP address? DNS will help you. How do you get DNS's attention? You send a packet to the transport layer. What? I thought you just said you couldn't do that yet. Well, not for what you want to do, but you can send one to the transport layer to get to DNS. Well, why is that? Well, because you were given the IP address for DNS up front. That was kind of like a starter thing that you got. So if you go to your network configuration panel and you look to see what DNS server you're using, there it is. This is the one that U of H gave me. If I go home tonight and look at this panel again, it will be different. it will be the ones that AT&T gave me. Or if I tether it to my phone, it'll be the one the cellular program gave me. Or I can erase all these and put in my own, like Google's 8.8.8.8 or 1.1.1.1. Those are popular ones. OpenDNS has some that are popular as well. But it's usually a good idea, if it's working okay, to use the one that you're given. But you never had to type this in. This was given to you automatically, and we'll talk about how. So that's why, even though I don't know the IP address of where I'm trying to get, the person that can help me, I do know their IP address. So I can call DNS. I put in a packet that goes to TCP, goes down to UDP, makes its way down across the network, and it makes its journey on towards the DNS server. And that's this guy here. In this particular case, there's only one DNS server for this institution, and it's the one called dns.poly.edu. There is not in this diagram a separate DNS server for the Computer Science and Information Sciences department. Some schools would have one. Our department might have one. But to keep it simple, they only show one. And this one sits at the edge of my network because this is the one that's going outside to talk to other people. So I also know not only is this the only one that I can get to on the inside, but this must be the official authoritative DNS server for poly.edu. This is the one that the whole world will come to with any question they've got about a poly.edu host. They can give me any poly.edu host name, and I will give them back the IP address. I must. That's my job. So when I look in a DNS record for Poly, and I say, what's the IP address of your authoritative DNS server, it will point to this host. It will point to this server. All right, but I'm also using it on the inside. That's fine. You can use it to handle requests from inside your institution as well. Very often you'll separate these, so if people start to beat the crap out of the one on the outside, at least it doesn't bring everybody their news on the inside. And there's some famous hacks. DNS is a very popular attack target. And we've, even in the last 2 years, have brought down big parts of the internet over and over and over with DNS attacks. Okay, biggest one, famous one is probably Dyn. It was a DNS provider. So my first place I'm going to look is actually not shown on the diagram except with this 0. The first place I'm going to look to see if I know the IP address of this is going to require looking in my own cache of DNS entries. This is not the web cache. It's not a cache of emails. It's a separate cache of just DNS entries that my operating system maintains. So it will go and look there first. This NSResolve will take care of that automatically. It'll respond immediately if it has a valid entry. So what makes it valid? It makes it valid that I looked it up before, and it still has time left before it expires. So very often, unless it's a super popular site, it'll be good for an hour. And as soon as you load it into your database, the timer starts, counting down to 0. It doesn't matter whether someone's used it or not. It just marches ahead to 0. Lots of times students think that if they access that entry in the database, the timer kind of resets back up to 60 again. So here's how to remember that that's a bad idea. You have a carton of milk in your refrigerator. It has an expiration date. One day before the expiration date, you go and take a drink. Does the date push itself out 7 more days again? Do you want to drink it again next week? And the week after that? And the week after that? If the date keeps resetting, you will. And it was nice knowing you. But that's why you don't want to keep resetting the date. You wait until it expires, you remove it from the database, and then you wait to see if anyone wants it again. If anyone wants it again, then and only then will you start the process over and ultimately result in putting a fresh copy back in your cache again. So there's interesting things that can happen in the meantime. Suppose I download a DNS entry and set the clock to 60 minutes for a site, a popular website, CNN.com. And 1 minute after I do it, and let's say it's the DNS server for all of University of Houston, and 1 minute after I do it, there's some big catastrophic fiber cut in Atlanta, and CNN loses access to its internet provider, but no problem, it has multiple connections. Wow. And so it immediately has the router switch over to the backup fiber connection. So they don't lose anything. Everybody at CNN can still get out to the internet. all the TCP connections that were there broke, but they get reestablished in a second or two. But the problem is that other ISP doesn't use the same IP addresses as the first one did. They assigned your router different ones because they plug in to different ports on your router than the first ISP did. So they can't both have the same public addresses. It would be like two houses having the same house number. So your IP address is changed. No problem. CNN immediately updates its DNS entries. It's all automated, in fact, and starts pushing it out to the top-level domains and everything else. So anybody who doesn't have CNN, the minute they look, they're going to grab the new address. Everybody's fine, except for you. You still have the old address in your database, and it has 59 minutes left. So for the next 59 minutes, no more CNN for you. You will not be able to access it. Nothing will change that until the time expires. So there have been a couple of approaches to try and fix that problem. One of them is to push small numbers out for popular sites. Like at my house, it wouldn't matter. I don't have a backup. So if somebody cuts my fiber, in fact, I don't even need somebody to cut my fiber. I just need AT&T to screw up the order and disconnect my gigabit Ethernet, which they did at 12:01 a.m. last Friday. So that led to ultimately a federal complaint I filed on Sunday afternoon, but not against them. Anyway, long story, rambling. I don't have a backup, so I don't really care if my DNS entry doesn't get updated. I can't do anything about it anyway. So that's one approach. Popular sites use small numbers. So if I go and look at the DNS entries for a site like Google, for example, that's what you get for eating spicy chips. You get the hiccups. All right, let's see here. I'm going to do a lookup. I'm going to go to Super Tool. Super Tool, here we go. All tools. DNS lookup. All right, let's try google.com. 5-minute TTL. Amazon.com. 60 seconds. Microsoft.com. 60 minutes. Interesting. Well, they don't like themselves. That's their choice to put that number in there, not anyone else's. What this basically means is they've got an arrangement sophisticated enough that they're probably using the other approach, which is an effort of an RFC. If one internet provider goes down, you immediately port your IP addresses over to the other one. So yeah, everything's different, but you lift and lay the numbers with command messages that move things over. So people are constantly working on initiatives to improve things like that. Down, bad, up, good. So that's kind of the idea. But it's interesting to see the numbers that people pick. The other thing that you might notice is when I asked for Microsoft, I got 5 different answers back with different IP addresses. And Amazon gave me 3, but Google gave me 1. Who has the most servers? Google. Yeah, by a mile. And then Amazon, and then Microsoft. So it's ironic that there are 5 entries for the DNS servers for Microsoft, and one way to distribute the load around the world is to give DNS more than 1 entry for the same host, which is a little different than giving it aliases for the same IP address. This is giving multiple IP addresses to the same name, and it will round robin and hand you out the next one. So the first person to ask gets this one, the next person's going to get this one, the next person's going to get that one, and they go back and around. So you can put 10 or 20 of them in there if you want. That's one way of doing load balancing to make sure the DNS load is spread across multiple sites. Yes. Okay. So that's one way to do load balancing. The other way to do it is just to push DNS entries close to the users that are different based on where they are. So what we did on Thursday morning's class, and I don't remember if I did it with you guys or not, we may have, I had them try looking up DNS entries for Microsoft, and I did it as well, and we had different entries. Everybody in Houston got the same one, and I got a very different one, and somebody was VPN back to their office, they got a third one. So I think it was Google. And so what that proves is same site, same one entry, but it's actually a different entry in the DNS database that's closer to you. So Netflix does that. If you try to go to the Netflix server, it's actually going to send you one that's geographically, topographically close. And it does that by looking where you are on the internet and handing you back a custom-built DNS entry on the fly that's got the IP address of the server that's closest to you. And you never know that's what's happening. Okay? So that's kind of the idea. So you can learn a lot by poking around with some of these tools. Meanwhile, all the way back here, the first place I looked was in my own database. If I didn't find gaia.cs.umass.edu there, I send a request to the DNS server that was in my list of DNS servers that I had in my network preferences. And to pull it up again, just to remind you, it's going to go to the first one. How interesting. I have to pick the right connection. I have to pick this one. It will show me, it will go to this one. It will send a DNS request to this. All right? He doesn't have it. So what he needs to do is to go and ask this guy. But not only does he not have the IP address for the host I'm trying to reach, he also doesn't know the host for the person who would know the answer, which is the authoritative DNS server for the University of Massachusetts. And in their case, they actually have one for the computer science department. So the diagram's not exactly correct because that's not who you would go to. You would go to the overall authoritative one for UMass, and I doubt the computer science department, maybe they are, but I doubt they're running the authoritative server for the entire university. You never know. Could happen. But I don't know that. So if I don't know this one, and I don't know this person to go ask, I'm running out of options. So how do I go find out what that is? Well, I have to go and ask the top-level domain DNS server for all of the .edus what the IP address is for the authoritative DNS server for Massachusetts. And then once I get there, then I can ask him, hey, what's this guy's address? So apparently this is claiming that I also do not know his address. Implausible, because I am also a .edu. I must know my own. So this is like my kin, right? But what this basically shows is I had to go all the way to root to figure out the address to go ask about .edus. In this case, I'm particularly interested in knowing the address for the authoritative DNS server for UMass. I get that answer back. I go and ask the authoritative server for UMass, and he goes, oh yeah, I know that guy. Here's his IP address. He hands me back the IP address for this host. I cache it here. So now I have a copy of it at Poly, and I send it to the person who made the request. And now he has a copy as well. He can put it in his local DNS cache. And the clocks start ticking down. Now I know how to actually open a TCP connection request, because what I've done is gotten the answer back to this. So now I can put the actual IP address in my socket request, and for the first time, finally send a message down to the transport layer. Later is kind of a Freudian slip, because the transport layer, if it's TCP, now it's going to try to negotiate a handshake with the other side. So I'm still waiting. All this stuff happens before I get anything done for my user. Their application's message has never left the machine still. So it will try and go into a handshake, and then we'll learn a little bit more about that. So this is called an iterative query. You contact the server, and this guy goes and goes to all the others necessary to get the answer. The other way of doing this is called a recursive query, and this one will suggest that each server goes and finishes the task for you. You ask each person once. I ask him, that's the same. He asks him, that's the same, but then he goes and takes care of the rest, and then the answer comes percolating back. The reason why I believe that's less common is the root DNS server couldn't care less about these guys, isn't going to cache it, doesn't want to be the center of all requests, doesn't want to have all these things have to pass through. So you're going to need lots of things to happen and cut a lot of this hierarchy out. So it's a heavy load. Okay, so we've been through all this. There's more slides to back it up that kind of walks you through a little bit. We've also talked about caching entries and how cache entries, once it learns a mapping, which is basically the IP address that goes with the name, once it gets the entry in the telephone book, it caches it. So TLD servers typically cache in your local name server. Root's not visited very often. That's why I said it was implausible. We go to root, we absolutely would know the IP address of all the TLDs. So I'd know exactly who to go to ask, hey, .edu guy, what's UMass's DNS server? And it would know. All right. Make sense? Okay, we looked at this already. These are the ones for, I'm not tired, but I've got yawns like all day long. It must be the weather or something, but I feel perfectly perky. I feel like I'm falling asleep. I maybe coming off a caffeine high. I probably drank too much caffeine. Anyway, here's the example for Google. I'm curious if I found something else with this URL, so let me go and see if I can get this to do something for me. Yeah, so what I did here was actually asked for mail servers, email servers. You'll notice this says MX lookup. This is another type of record in a DNS server. The one that we looked at so far was an A record, which is the IP address of a server, but just a general computer. This is a particular type of record for the servers that will respond to SMTP requests. They should be the only ones you use. And if you get an email that claims to be coming from Google, it needs to be coming from one of these only. If it comes from anything else, it's fake. Drop it. Close the connection. Add it to your spam list or something. So there's IPv4 addresses and IPv6 addresses in here. So it's really kind of half the numbers because these are the same host. The first one with a IPv4 address and the second with a version 6 address, which looks very, very different. Okay, we can also do a blacklist check. So let's go to uofh.edu. And you guys have seen the whiny notices on our homepage about Yahoo's not forwarding our emails. You've seen those out there. Well, it's self-inflicted, totally. We've lost control of enough servers on campus that people have hacked and used to send spam to Yahoo users, that enough Yahoo users have clicked as spam, that Yahoo has figured out that there's a lot of spam coming from our network. No, but that's the one that we're talking about on our website. So they basically filter out, force us, all of our outgoing email into a queue to wait 5 days or 4 days or 2 days. And hopefully that makes it less fun for the spammers and they move on. But in the meantime, it makes everybody's outgoing email to any Yahoo address take forever. So people go like, well, I'm not sending spam. Well, how do you know the server that is sending the SMTP message for you hasn't been hacked? Show of hands? How many people know that? None of us know that. So it's the email administrator's responsibility to keep those systems secure and free of hackers so they don't get hijacked and used to send spam. When they do, then it, of course, affects everyone who uses that server, including us. So if we go to uofh.edu, we get a whole list of these things here. For one thing, we've got like a ton of email servers. That's problem number one right there. That's like this many to manage. Okay? And if we do a blacklist check, I don't know if I actually clicked on that or not. Everyone thinks we're good. CASA did not answer. So these sites are names of sites that compile spam flags. So when you click on the spam button in your email program, on your phone, on your tablet, on your laptop, wherever it might be, it ends up in one or more of these people's databases because they buy the data. And then they turn around and sell the data to people that run email servers. So they can check by looking at these guys, hey, I just got an email from uofh.edu from this IP address. What are the odds that it's spam? Low. All these guys are basically reporting, I don't have tons and tons of people complaining about spam from uofh.edu. All right, well, let's go look at a different U of H server. Can't do that if I make it go away. What did I do? Let's do MX. MX. Not the one I want. Here's MX. Here it is. I'm going to do it. There it is. You can pick a different one. This server says that that's a spam server. So if anybody believes this, anybody subscribes to this particular database of likely spam servers, they will be suspicious about accepting email from it, or U of H or anybody else it portrays, if they accept it at all. So this is what gets us into trouble. I used to have a lot of fun checking with people like people that I knew were bad email spammers, like the University of Mexico, but they've cleaned up their act. They basically outsourced it all, I think, to Microsoft. They let Microsoft run their email for them, which is not a bad idea. All right, back over to where we were. Interesting, guys, learning some tips and tricks and things. Okay, does the blacklist and whitelist stuff make sense? You understand how that works? When you click on spam buttons or their filters capture spam traffic, it raises your spam ranking, which is not good. And at some point you cross these spam list thresholds and they mark you with an X. And they go, spammer. And then people stop accepting emails. So A records are just regular, ordinary, run-of-the-mill records of IP addresses for host names. NS is a name server record. This is the one for DNS specifically. MX is for mail servers specifically. And a CNAME entry is just an alias for an A entry. So you could have www.walmart.com as a CNAME for walmart.com. You could have w3.walmart.com as a CNAME for walmart.com, and lots of other versions as well. Some sites used to actually support those, like w3.newyorktimes.com, and it doesn't know it, but I can go there, and I can just go to New York Times, and it will also resolve it to www. DNS does that. All right, and I've showed you guys the question before on abuse and I forget the name, spoofing, I think. It's not the right name. And what people do to try to keep that from happening. Like, have I shown you Walmart with a hyphen? That's not their domain name, you know. The domain name is Walmart, one word. So what do you think Walmart wants to happen if somebody types it in with a hyphen? You would want them to redirect it. So do you think when they figured that out that wall-mart.com was still available as a domain? No. So how then does that happen? Exactly like you just said. It redirects to walmart.com. They filed an abuse complaint with the Internet Corporation for Assigned Names and Numbers, and they went through a process and basically alleged trademark infringement. Sometimes they have to go to court and get a court order and present it, and ICANN will take their domain name away and give it to Walmart. They have to pay to register it and all that, but people early on used to do domain squatting, cyber squatting. They would park on all kinds of trademark names. It didn't work. You would go to their site and you would find something. Then they passed rules that said you can't squat on a domain, you must provide a service. So this is why when you go to something like, you know, a site that used to be around but isn't, what you'll get is an ad, he says, with feeling. Hello? Hello? All right. How about Amazon? Well, there it went. Now it finally did it. All right, so this is an ad. Now, this is the company that owned it before. Amazon.com went to Amazon.France, which is really interesting. Amazon. I guess it sounds like Amazon. So what if we try a different one? Amazonian.com. All right. We do not want to go there. All right. Well, maybe you do, but yeah. Amazonia. Yeah. Hey, if you pick a word that's close to a site that people go to, it's just more money. People will do anything out here. That's trying to load something. God, I have to be careful. Amazon. That's kind of a funny one. Amazon. All right, so here's an example of what I was trying to get to. They could be torn down for having the site because it's not providing a service, obviously. What it should do is provide, these baloney search requests and links to other sites and make it look like it's some useful directory page or something. Perfectly legal, perfectly legitimate. That's a service. So if you spell something Wamlart, I'm making this stuff up, all right? So, if like something illegal pops up on the screen, I bear no response. Look, it took me to VerizonWireless.com. How the hell do they, Wamlart goes to Verizon? Okay, whatever. Yeah, it's just like somebody had a lot of fun with that. We used to do a bunch of really fun, weird ones to try to capture all that extra stuff. And there's sites, there's companies you can pay that will collect the DNS misses. They will sit next to a big DNS database and look for all the entries that come back with no such entry. And then they will sell those to you. And you can look for the ones that are variations around your site, or look for the ones that they went to right after that, after they realized they misspelled it, and buy those and grab them too. So you can be smart about it, about the way you go about it. Like how much you want to bet that takes you to Apple? What do you think? Do you think it will? iPhone, Phone. When I worked for Southwestern Bell in 1976, we had entries in the telephone book for the phone company, spelled with an F, for people that needed to call us and didn't know how to spell it. So that blew my mind for a while until I got older and realized that's actually a very good idea. So that's not going anywhere. How about iPhone.com? All right, that's valid. That's a valid site. It's for sale, but it does have a search field and stuff like that. iPhone.com, of course, takes you to Apple. What about iPhony? Yeah, Sound Strategies. Who knows? All right, I'm getting increasingly nervous, so I'm going to stop. Yeah, I wasn't expecting the Amazonia one. I have to check that out later. All right, so DNS protocol is a data structure. You put data in the fields and send it off. Just like every other HTTP data structure had certain format, but this one is starting to look a little bit more like a network protocol. HTTP was a little free form. Yeah, you got a GET and a POST or something, and you got a bunch of variables with values and a bunch of body stuff. This one's a lot more rigorous. So you've got specified fields for things, and you've got questions, and then there's a place in the data structure for the answers to go when it sends it back. So this is sent back and forth, and you just fill in blanks in here as you go along. So that's one way of doing the protocol. What some other protocols do is you send them one data structure for the question, and it sends you a completely separate data structure for the answer. However you want to write the code. It doesn't make any difference. So you can take a peek at one of these. This has a list of your questions in here. This has the count. The records are listed in order in response. If there is authoritative servers that come back as part of your answer, their names will go here. And then sometimes there's a variable number of records with extra info. How do you update DNS? I talked about the need to do it whenever a site host goes online or your internet outage occurred and you needed to switch over to the other ISP or something like that. But you will register a name with your DNS registrar. If the domain name already exists, which is the last two parts separated by a period, like tx.us or amazon.com or tech.mx or whatever it might be, then you already have a DNS registrar. You have somebody that's running your authoritative DNS server. You log in and you add a record. So for example, if I want to go to GoDaddy.com and log in. All right. This guy looks like somebody I would so get along with. Doesn't he just look like a guy that you could, in a heartbeat, watch a football game with or crack a joke with? They could not have found a friendlier looking person if they tried. And I can't figure it out, but I would love to meet that guy. Like, and I'm sure he's a real employee, knowing them. You can call him up on the phone, and sometimes I'll call people on the phone and go, like at 311, do you guys ever call 311 for the city of Houston? I'll call her up and go, it's you. It's the voice. You're it. She goes, yeah, it's me. Good ear. I'm like, I knew it. You're the lady that I have to wade through with my little call prompt thing first. And so some of these people are actually very famous. There are superstars in that field, believe it or not. And if I get a chance, I'll talk to you about one in a minute. So here's some of these out here. I can go to DNS for any of these that I own and pull it up. Here's some A records that I've got. Here's a bunch of C names in here as well. So if you go to photos.golfghostshots.com, it sends you to smugmug.com. Do you guys know what that is? Smugmug is a photographer hosting site. So if I go, let's try it. If I go to photos.golfghostshots.com, it keeps the branded domain, but this page is being coughed up by smugmug.com. And it even says it right here in the corner. Right, so, you can burrow down through here and do all that stuff, and we can get to like Friday night's big basketball game between Kincaid and St. John's. Anybody here know either of those schools? Well, let's just say that for the first time in many years, St. John's beat Kincaid, and it was pandemonium, the last pitch of the game. That's the headmaster's son, so Mom will be buying that picture of it. All right, so you'll notice the URL never changes at the top. It always says golfghostshots.com in there. So you can have a custom domain that is fed by someone else's site. None of this is really, there is no such thing as golfghostshots.com. It's just a domain parked at GoDaddy. If you go to order.golfghostshots.com, then it goes to a site that is parked at GoDaddy. FTP, same thing. Event goes to this one. So this is one that's a domain shortening site that I paid, so I could do GSEE.es for GCS, Golf Coast Shots, a really short one. So you can play around with stuff, and I do this stuff just to play with DNS, 90% of it. So that's kind of the stuff you can get. If you don't have a domain name yet, you buy one for $1 to $100, whatever it might be. And it always comes with the DNS server. They will instantly set it up and put up a parked web page. Before you do anything, it will automatically have a page that advertises the hosting company that you just bought the domain from, just like the GoDaddy ad we saw 10 minutes ago when I went to one. So here's a couple of entries they've got in here, one for the name server, one for the main host. You must have both of those in there. They're required. You should have email if you ever want to get it. Stop it. No way. Hide. Thank you. Okay. How do you attack DNS? So DNS is a very popular vector for attacking servers. And if I pull up a couple of these, this is also a little dangerous because I store all kinds of crazy stuff that are good examples of network problems. And some of them are tasteless. Okay. Which one am I looking for here? Dyn. Let me see if I can find this one. Okay. Okay. Yeah, so I may have talked to you guys about this before, but what I want to look for is Twitter, image, outage, DNS, Dyn. And see if I can find it. Bingo. So this is one of the graphs that was produced to show the DNS requests that were not able to be satisfied because of an outage at Dyn.net. And Dyn.net is a wholesale DNS provider that ISPs will hire to keep their DNS servers updated. So they don't bother doing any of that themselves. They let this third-party company do it. So that company controls what gets inserted in, say, Telmex's DNS servers and a bunch of companies on the East Coast. So Dyn got attacked and got taken down with a denial of service attack. A denial of service attack basically took 100,000 Internet of Things devices running a version of Unix that had known bugs whose owners never bothered to patch them and were on the Internet and therefore accessible, and loaded code on them that at the appointed hour and time all woke up and started sending requests to Dyn.net. And so overwhelmed it that their servers didn't have enough bandwidth to respond to the legitimate requests. It was like 99% of the requests coming in were these fake ones that had to be serviced, and a tiny 1% or less were the legitimate ones. So what does that mean? Well, somebody was going to Dyn.net for a reason. One of their customers, let's say it's Telmex, needed an entry that had expired or wasn't present before in their DNS database. So their master DNS server tries to go and get the update from Dyn and does not succeed. So the user doesn't get a DNS entry sent back, and they are not able to obtain the IP address, and therefore they cannot open a socket call, and they cannot make an internet connection to that site. They're down for that site. They may have other things still in their DNS cache. The DNS server for Telmex may still have things in its cache. They have a bunch of them, but they're all expiring. And as soon as they expire one by one, they are not getting replaced. So the internet gets smaller and smaller and smaller. And within 5-10 minutes, you saw how short Google's and Amazon's were. They only wanted theirs in there for like 60 seconds. In a minute, no one can get to you. Nice job for cutting it down from 60 minutes. So you can get burned by doing that as well. You can become too dependent. Caching is not considered harmful. You should try to cache entries. So what some people do, what some people did to overcome this, they would go to a buddy's DNS server and say, quick, FTP me your DNS database. It's like 85 meg. I'll do it now. So you FTP the thing over and hard-code it into your DNS database with an infinity expiration date for the entries. Yeah, so entries are changing all the time, and so as soon as you do it, things start getting old, but the big ones do not. You will have Google, Amazon, all the popular sites, they're not changing their IP addresses. They may want you to go to a different IP address, but if everybody insists on going to that one, at least it will work. So you can get your way around it, but for better part of half a day, a big chunk of the hemisphere was down, including a bunch of Central and Latin America, but you know, we don't have room for those on our map because the web page is only that big, so we can't possibly put anything other than us on the map. We also still insist that Hawaii and Alaska are islands off the coast of Baja California. So like you did on maps the whole time. So it's funny how we don't like to change stuff very much. Okay, that picture was scaring me, that guy. So Wired wrote up a little bit of story on sort of what was going on. That was a major boneheaded move by Dyn. Cost them a lot of business and should never have happened. That was very poor management on their part. Now, we go to GitHub, who also had an attack. It was not a DNS attack because GitHub is not a DNS site. But GitHub has also been kind of a popular attack site, and they survived, at the time, the biggest DDoS attack ever recorded. 2 weeks later, there was one that was a little bit bigger, being rumored, but the person who was being hacked never came public, and that story never made the news. But what happened with GitHub was they had tons of users launch an attack against them. GitHub is one of these sites who distribute open source software, but they also will give you points for publishing good entries on blogs and penalize you. And so if you mess around, you can get yourself kicked off pretty easy. They're pretty ruthless. I don't know if you guys have read like any of the Stack Exchange forums that you find in Google. So maybe you guys know this site, Stack Exchange. They have a ton of They have a ton of topics that they cover, but you know, just pick one. Like let's Google for how to clear contacts database from iPhone. Let's do something like that, and we see the worthless Apple discussion ones. And if we're lucky at all, apple.stackexchange.com made the top page. Just got an iPhone 7. Your question is unclear. So the criticism begins right here. Can you edit it to tell us what apps you're using? Blah, 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 blah. Go to settings, do this. All right, we can pick up another one. No, but it can. So if you post something that's stupid, it's just like super easy to, like, how to get Excel to calculate 2's complement number. All right. So that would, here, very first one, Stack Overflow, similar kind of site. Okay, they put some things in here. When I copy your part, I get an error. You may need to use semicolon. Again, so nice. Usually when you pull these things up, it's like, you obviously did not read the forum posting rules before you did this, and your question is irrelevant or not in the wrong area and has been closed for further discussion -6. And then, like, you get pulled down in there and, like, you get thrown off the island. And, like, I have never made enough points to post a frickin' thing on these things. I don't ever post stuff anyway, but it would be nice to once in a while, but I'm so scared to, you know. So it's funny. So that's what I think was probably behind GitHub, is they, like, kicked off the wrong guy, and he goes, I'll show you. And so he loads up and drops a 1.35 terabyte per second attack. Yeah, that's a terabit, excuse me. Don't want to exaggerate. Terabit per second, only 1/8 the size of a terabyte. And it lasted less than 15 minutes. How? What did they do to survive it? Well, fortunately for GitHub, they had a mitigation provider. It's the same provider that does lots of content distribution networks, Akamai in this particular case. And Akamai, their mitigation, DDoS mitigation service was activated, and within moments, they started pushing DNS entries into their servers all over the world that sat at local ISPs to redirect traffic bound for this address to instead be redirected towards a local server, where DNS would just send the bits to the floor. And it would never make it onto the backbone. It would never make it onto the ISP's network, let alone ever get to GitHub. So, you know, they had enough servers around the world that at any given ISP, there weren't enough people trying to attack GitHub that the server just couldn't shunt the traffic. And then they got smart in just a few minutes at figuring out exactly what the fingerprint was. Like, what's different about these requests, these packets, than all the other legitimate ones? Ah, these are all 69 bytes long, and they come from an IP address that ends in a 4. Okay, update your filter and just filter those off. So all the good traffic now is passing through again, and all the attack traffic gets sent to the bit bucket, and within 15 minutes, they gave up. They stopped. So that's considered an enormous success. So if you go and Google, just to show you how opportunistic we are, DDoS Akamai attack. Let's see what happens. We'll go to Akamai. First thing is an ad, Akamai DDoS protection. So we'll click there, and let's just give it a minute, and we'll read through here and look a little bit. You notice they put a number at the top. What I'm waiting, here we go, under attack. So usually what pops up is just like, are you being attacked now? Do you need help? We're here to help. Click here and dial this number. So they're like right on top of it. This is something where you'll call in an emergency and get help from people. So contact our team, have us call you, put your name in, stuff like that, and they will. They'll call you immediately. And they have a team of people. So there's a bunch of companies out here that will do this. What you should do is basically have an insurance policy, have a mitigator under contract, and you usually will if you also are distributing things with a content delivery network anyway. It's one of the things a CDN can do because they have servers right where they need to stop this stuff. So Akamai figured out like that's a whole other area of business for them. So if you're attacking GitHub, Akamai is going to try to get in your way. Kind of neat. Takes all the fun out of it. So DDoS attacks essentially are bombarding a server with what appear at the initial state to be legitimate requests. So in this chapter on DNS, it's basically trying to send DNS requests. Hey, what's the IP address for Google? Times 50 million times in a minute. If you can get enough servers to attack, then you can bring it down. So they've tried to bombard the root servers, not successful to date. You know, so that I don't think that's true anymore, by the way. But at least they were smart, like, well, to date, it's all going to get attacked, and the attackers get bigger. So one way to survive this is just to make sure you have more places to attack than they have people to attack you. Like, okay, you're going to send 10,000 marchers to try and shut down 7-Elevens. Well, guess what? I have 11,000 7-Elevens. So 1,000 of them, you're not going to have anybody in front of. So that's as simple as that. You just try to outgun the attackers. And so one of the things you can do if you're being attacked is spin up 20,000 servers at Amazon Web Services. Yeah, it might cost you $10,000, but the attack goes away. And it takes all the fun out of it. So they get better at doing it. You also can bombard the TLD servers. That's a little more dangerous. You also can have different types of attacks, like man in the middle, where you receive the DNS request before the real DNS server does because you're between it and the user on the network. Like you insert a router on the network and the traffic will not pass through you unless you let it. So you very carefully pass everything through as fast as you can so nobody's wise. You don't publish any routes, you don't try to update, you don't respond to anything. And except when a DNS request comes through, you give it a fake answer. And you have the user go to wherever it is you really want them to go, like something that looks like Chase Bank, but isn't. Or something that's a pass-through filter, which then goes to Chase Bank, pulls the objects back, paints them for you. It looks like Chase Bank because it's their objects, but there's an invisible frame in front of it that you're actually typing everything into. For example, there's ways to keep that from happening. DNS poisoning is send bogus replies to the DNS server, which it will cache, or send bogus relays and things. Stuff it with incorrect entries. So you can try to poison it that way. And then you can use DNS to launch a DDoS attack. You can send DNS a query that says, please send me everything in your database, or send me 10,000 things out of your database. And you spoof it as to who's asking for it. So DNS will go, here you go, and it'll start throwing those at the server that you said wanted it. And so what you're getting the DNS server to do is flood a bunch of data at this poor server that never asked for anything. And so that's an example of an amplification attack, where you send very little and you cause somebody to send very much someplace else. The GitHub amplification, GitHub attack I showed you was an amplification attack. And at its peak, I think they had 50,000 to 1. So they were able to get other people to attack the site for them. Okay. How are we doing on time? We're getting there. Okay, we want to try and talk a little bit about point-to-point applications and then see if we have some time for video streaming. But video streaming, I don't know if I want to cut it in half, so let's see how far we get. The type of architecture we've talked about so far has been client-server. Everybody goes to one spot. So we've looked at lots of things to make that scale, like duplicate the servers, round-robin DNS entries, have more than one site, give custom DNS responses back based on where the user is, and on and on and on. You can have something come into a special type of server that is super fast. All it does is network connections, and it will do a TCP redirect. So it's like the maitre d'. You come in and it will just point you to a table. It doesn't have to do anything other than that. So load balancers are types of devices as well. But with point-to-point architecture, it's much more of a distributed environment where there's no one at the center, there's no designated server, there's no one in charge. All the connections are among peers. So like BitTorrent, for example. Well, there is a little bit of server going on with BitTorrent, because somebody has to tell you who all the sites are that have all the chunks that you need, but very minimal. And there have been some of those that have been taken offline, defunct, sued, etc., because they've been used basically just to steal copyrighted material, for example. These P2P architectures drive telephone companies crazy because their networks are architected for most of the traffic in one direction, from the servers down to the users. You send a little URL and you get a bunch of data back. So they can split their network so most of the signal propagation is downstream to you, like ADSL and cable modems. So when you start moving things around and the sources are out at the edge, then it makes it harder. It saturates their network. It makes it harder for them to keep up. But VoIP is an example of this, as well. Okay, so client server versus point-to-point. If you have a server with a file of size F and you are trying to send it out to n different peers, then the peers' download capacity becomes the limiting factor. So how long before they all have it? It's going to be the slowest one. So if somebody's on a dial-up, it's going to take forever. So it increases linearly by the number of users you've got. So this one server is having to send things. The more people you have to send it to, the bigger this denominator becomes. Of course, obviously. 10 people are trying to download something, it takes longer than if one person's trying to download it. Okay, with distributed P2P, then the connections are different. It's basically the max of whatever your slowest one is, or basically to increase linearly, you've got to aggregate the bits, and your max upload rate is a combination of what each of them can do. So everybody can gang up and send the user a piece of the file. They are the only limit themselves, not the server anymore. So you can actually go much, much faster than the server if you have a big enough connection to handle all the incoming stuff. Okay, so that's a little bit with that. Examples, it scales really, really well, and the distribution time is basically linear. BitTorrent is an example of a service that divides things into these little chunks, and the chunks get distributed around the network at BitTorrent participants. A master file keeps track of who's got what chunks. So when it's time for you to get your file, your illegally downloaded movie, you get pieces, and the software goes and finds where the chunks are. And if you want to continue to be serviced by that torrent, you must then take chunks and make them available for other people to download. So the technology is actually kind of interesting because they have starvation and gratuitous transmission ideas. So let's say Alice shows up, she gets her first list of peers from her tracker, then she can go out there and begin to open connection for these guys. And at the beginning, they're willing to do it. They're willing to send her packets, but if she doesn't reciprocate, they're going to starve her. They'll choke her off. They'll stop sending her things. So lots of people come and go as this happens, so you have to constantly be willing to lose connections and to find new peers. And you can either be altruistic and stay in the torrent, which we hope you do, or be like me, not selfish, more scared, and just leave as soon as you're done. So at any different time, different people have chunks. Tit for tat is the name of the scheme, where I'll give you some chunks if you give me some chunks. There's also something called optimistic unchoking, which is sort of a bizarre name, but it basically means like every 30 seconds, you will randomly select someone who's on your do not send a Christmas card list and try sending them something, offering them chunks, because it may be that they're in a different situation now and they become a very big provider to you. So that's what's shown in this diagram, where Alice just tries to let Bob in, salut, to get access to chunks, and as soon as she does that, she finds that Bob is a gold mine, because Bob has access to these other users in behind that have lots of data that Alice is having a hard time finding. So they have some interesting algorithms for how to explore and try to make new friends. This is like the lunchroom or the playground. You just try to make a friend and see what happens. So you may end up with a much higher upload rate opportunistically. Okay, we do have a little time to start talking about CDNs, and we've talked about these some already, but they are, in lots of areas, the #1 major consumer of bandwidth on the internet. And I did my part last night, watching an assigned Netflix video from a class that I'm taking, and they have lots of interesting ways they deal with the huge volume that they need to put on the network that the network really can't handle. And one of the things they try to figure out how to do is put copies of their data in remote areas. So they have a distributed application layer infrastructure. So we'll stop with that and switch gears a little bit, and then we'll pick up on the rest of this stuff on Wednesday. One of the things you need to understand that's very different about delivering video on the internet from delivering it in a normal broadcast network is you do not want to use a fixed amount of bandwidth all the time. When you are given a license to broadcast a television or a radio station, you began that journey 75 years ago with a constant dedicated amount of bandwidth. You had a license, you were the only one allowed to use it, and every frame of image you sent used the same amount of bandwidth. So there was no reason to try to compress or delay sending things or copy or anything else that might reduce the amount of bandwidth, because you had all you needed. You had exactly what you needed. You had no more, but no less. When we try to put this on the internet, those are dangerous assumptions. We want to try to use as little data as we can. So one of the things that algorithms do that is happening like with WebEx right now is they are taking snapshots with a camera that they hope is good enough quality not to introduce a lot of noise. Noise is represented as being told that the brightness and color of a pixel is different than it really is. So if you're fibbed and you're not told, then you may miss out on noticing that this whole block of pixels in the area are exactly the same. If I told you that, you would come up with a much more efficient way to transmit that news than sending each pixel one by one by one. You might say, send this pixel 100 times, for example. That would take a lot less time than sending. But if there's a lot of noise in the signal, that makes it harder for you to detect and spot those things. So there's constantly this race. So what they're showing you in these two images here are two sequential frames of a video of somebody running at sunrise across a field, and very little changes in this picture. Maybe the breath that they're breathing, if it's a cold morning, looks different. Maybe the position of their hands and arms are a little different. But if the camera that filmed it was good and the digitization was decent, then everything else is pretty much the same from one frame to the next. Some things in the frame simply slide, move, like the blades of grass. They're moving left to right, but they're not changing unless the wind's blowing. The sky looks like it's not moving at all. It's just kind of a constant shade of purple. If I follow it long enough, it gets brighter as I get pointed towards the sun more. And the silhouette's black the whole time. So I don't need every pixel of this to be transmitted to get the news across of what's going on. So what I might do is build myself a budget. And depending on what the algorithm is telling me at a given time, I have a certain amount of bandwidth. And one way to represent the amount of bandwidth I got is to give me a packet to fill. And because it's video, I want to send a packet every 50 milliseconds. No slower than that. If I start sending packets less than every 50 milliseconds, then it starts to look jerky. So how big of a packet can I send every 50 milliseconds? Well, that depends on the bandwidth of the network and the congestion and everything else. Right, so figure it out and maybe send it a slightly bit less often, but at least tell me how big the packet is. All right, here's your packet. You have 4,000 bytes in this packet you can send. Not bad. Not bad at all. So what are you going to send in the 4,000 bytes? Well, if you send the entire picture, it's going to be really low resolution, like a YouTube video. And we've looked at these before, but just to remind you, if I go and look at a YouTube video and we do something like University of Houston Cougars basketball versus Cincinnati. Here we go. That's an Oregon one. That'll work. All right. All right, so this looks pretty good. So the first thing I'm going to do is move my video out of the way. And I'm going to switch my resolution down to 144. And do you see the difference in quality? You can't really read the letters under college basketball anymore. You can't see what's on the T-shirts. If I make the packets bigger, go up to 760 again, now it's crystal clear. You see that? So this is the same kind of audio, the same number of, maybe the same number of packets per second, but greatly compressed, as if I had much less bandwidth available. So what I want to do in this picture is figure out the stuff that's important to send and the stuff that's not important to send. Well, what does it mean, not important to send? It means to say, just repeat what you did on the previous frame. So like this is the same between here and here. So I get a very low change score. These are low change scores. Down here, some ones in here, but then the rest of this is zeros. I see lots of change here. I see change here. This change, this is super tough to do because it's blades, but these over here are just sliding. So you just mark all these. This is one way to do it. Put a grid and give it a value for how much it's changed. And the ones that change the most, you start by filling your packet up with those. And once you have those filled up, then you move to the ones that change the next the most, and then the next. And what you hope for is that you get to most of them. But I didn't. That's okay. The next frame, you know, I'll try to see what's changed. Here's the problem with this. Error accumulates over time. So if you spend all of your time prioritizing the things that are changing every single frame, you will miss the things that change gradually because they will never score high enough to make the cut. And so what you'll find after a minute is this person's silhouette is running and there's like water underneath and a building and still blue sky. Like it doesn't make any sense. You've got pieces of multiple images stuck together that make no sense. The other thing that happens with these is periodically you will stop what you're doing and you will completely retransmit the frame from scratch. And they call those keyframes. So that's specifically to eliminate that problem. Sometimes if you start watching a video between keyframes, the only information you're going to be getting are the deltas, the changes. So it'll look really, really strange. You'll see some things updating, but the rest of it looks really strange. So let me see if I can find a keyframe. Here's one here. So here's a movie that I snipped off of YouTube between keyframes. So if I don't remember how to do it with this stupid app, but you can see, I'm going to play it for you. It starts off, and I had to like do this 100 times. It starts off, and it's like an ad. And I'm going to lose a keyframe in here. Let's see if I can get it to work. I have to do it a bunch of times to make it happen. And then I eventually, I think I succeeded. So what I'm trying to do is back it up to a spot where I'm between keyframes, and all I'm getting are the changes like in the tires. But I actually wonder if this is the right movie because I think I had more success. I'm looking at the right image. It was this scene. There you go, right there. All right, you see? I grabbed it where I started off after a keyframe had been sent. So the only thing that's happening now, frame by frame by frame, are the changes from the previous frame. I have no base to start from. So what this is basically telling me is this is a little darker than it was a minute ago. This is a little darker. This stuff hasn't really changed. None of this stuff has really changed here. I've lost most of my chroma, most of my color. Paint this a little more red, paint this a little more yellow. Most of this other stuff's not changing very much. I can move through. Like this, I've added some color to this. And at some point, I'm going to go through and I will get another keyframe. So like right here. And that's a perfect place for one to happen because keyframes are big. They're big bandwidth consumers. So you'll use that to send the whole picture. The problem is that people are so spastic with the way they make videos now that you force lots of keyframes more often than your network can really handle them. Yes? Both. They will be sent on a periodic basis, like clockwork, but they're forced to change when everything's a 5. You know, you like switch scenes and everything scores, you reach a certain threshold and you go, screw it, send the whole thing from scratch. There's no way, it's just going to look confusing. So a great place to see this is in commercials. So let's look for a Nike commercial. Let's see if I can find one here. Dream Crazy? I don't know, this might be one.
Picture OBJ wearing yours.
All right. Change in scene. Change in scene. Change. 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 You're killing me. Change. 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 Oh, that was as much as one with the sun popping in. Another change. Change. So these are hard. And sometimes they're like super tough. Another change there. Zoom out. Another change. Another change. So if you want to find stuff that's going wrong, you can look immediately after keyframes and you'll see it struggle to kind of keep up as things are moving around. All right, so that's enough for now. If I can find some more zoomed in ones, I'll show you what's happening around the edge. The JPEG standard, has anybody ever read it? Or the MPEG standard? They are like kick your butt hard. They are really deep. So if you ever have an interest in learning exactly how JPEG does this stuff, and you think, I'll wait till the weekend before the assignment's due, I'm not going to give you one, don't worry. It's like way above this, but just make a note, you're going to need some really quality time and a pot of coffee. It's tough. Some of the algorithms they use in there are really, really clever and not at all intuitive at first for the way they measure changes. So those guys, you know, Joint Photographic Experts Group, they're not kidding. All right, guys, thank you very much. Have a great couple of days. I'll see you online on Wednesday. I missed a chat. Let me see what the chat says in here. Nice mug, nice mug, nice mug. Oh yeah, okay. They can sell it. Yep. What happens to defunct companies? Depends on who owns the trademark. If they abandon the trademark, anyone can get it. Usually, a bankruptcy court will award the assets to a trustee, and they will hold on to some money to kind of maintain, settle, respond to things, deal with creditors, kind of like probate.